Hey again, everybody. This video, we're going to talk about one of my favorite topics when it comes to microservices is how do microservices communicate with each other. So why don't we take a look here? We're going to review the microservice layout that we're going to be building out in our application here. So up to this point, we've really concentrated on those first two, and really in a very minimalistic way, we have our catalog microservice and our inventory microservice. And I mentioned that whenever a new product gets created in our catalog, we want to be able to notify the inventory microservice because the inventory microservice now needs to start tracking inventory for that product. Same thing for updates and deletes. And the other thing is we can imagine that if somebody is querying the inventory service to say, what are the inventory levels of product XYZ, where if XYZ is the product code, that means that when we send that query up to the inventory service, because within a microservice, we do not want to leave its boundaries to answer the question. So we won't want to be forced into a situation where we only have the foreign key for the product stored in the inventory microservice database, because that would mean in order to send back the name and the product code in our payload response, we'd have to make a call into the catalog microservice. So we don't want to be doing that. So that means ultimately that when a product gets created or updated in the catalog microservice, there are certain properties like the product name and the product code that we're also going to store in the inventory microservice. And that can seem a little counterintuitive at first because we've been taught with normalized databases you don't end up duplicating data, but in microservices it's absolutely very common to do this. We want the microservice to be able to respond without having a dependency on other microservices because we don't know if they're totally up and running. Like one of the big features of microservices is resiliency. So even if our catalog service is offline, either because of maintenance or an unexpected outage, we'd like our inventory microservice to continue working. So, all right, with those things in mind, just reviewing again those pieces, I wanted to touch on again the distinguishment because in this video we're going to talk about integration events, but I wanted to make sure that we again just distinguish them from domain events. And they're very, very similar in that whenever an aggregate ruler entity wants to inform someone that something of interest has occurred, it's going to send out an event. So in the domain event, the difference is the domain event does not leave the bounded context. Bounded context being the domain-driven design name for it, and we can basically say our bounded contexts are our microservices. So if something of relevance occurs that we want to notify others within the same microservice that it has occurred, that's a domain event. So we issue it, and it also gets handled within the same request response transaction. So before we send back our response to the client with whatever call they've made, we're going to handle all the domain events that are also part of that transaction. Whereas integration events are for crossing bounded context, or in other words, crossing between microservices. So whenever we want to communicate something of interest between microservices, we're going to use integration events. And the integration events, you can see the approaches and the verbiage here is almost exactly the same. This is however going to use a publish and subscribe approach. And when we throw an integration event out on our event bus from the microservice, so in our catalog service microservice example, we'd be putting out like an integration event for a product created. Once we send the event, we're not waiting for it to be handled. We don't even know who's on the other end listening or cares that that event has occurred. We don't know. So from the catalog service perspective, it can go ahead and now respond back to the client saying, okay, here's your response. What other microservices care about the event will handle that, in due time. So there's no waiting for those events to actually be handled when it comes to the integration events. So that means we're going to have some sort of messaging service like RabbitMQ or Kafka. And yeah, so again, just come back real quick. So whenever we want to move between microservices, so if we are in this case talking between catalog and inventory microservice, we're going to be putting integration events out on our event bus, which is on the far right there. Domain events stay within the microservice. They don't go out to the event bus. Now, the really interesting thing is, and this isn't necessarily a requirement, but I think it's makes a lot of sense to do it this way. When we want to send an integration event, so product created, the way we're going to do that, and we'll see it when we actually get to the coding exercise in an upcoming video here, that what we're going to do is we're going to first put out a domain event. The domain event will be product created, but within the domain event handler, that's where we're going to say, oh, well, one of the things I want to do in response to that domain event is create an integration event. So they sort of piggyback off each other, and we'll see that. All right, rules for microservices state. Again, just trying to reiterate why we need integration events. Each microservice has its own database, no shared databases. So when I was talking about sharing out like the product code and the product names, the inventory microservice will not and must not have access to the catalog services database. Therefore, it can't rely on that database to get the product codes and names. All communication between the microservices is done via asynchronous messaging, i.e. on our event bus. And when responding to a request, a microservice does not need to make HTTP calls to any other microservice. And that comes back to the point that I was making earlier, that if a request comes into the inventory microservice saying, hey, what's the current inventory level for product XYZ? And in that response, we want to send back the product name along with its inventory level. We don't want to be making an HTTP call from the inventory microservice over to the catalog service to get the names of the products in real time while we're responding to that request. Hence, that's why we're using integration events to basically copy data over so that the inventory service can respond on its own. It doesn't have to rely on making calls to other microservices to fulfill the request and the response. Keep microservices small and cohesive, and then use domain-driven design bounded context principles to identify microservice boundaries. So just wanted to repeat that. That's a repeat slide, but I thought it was important just from driving home the point of why we need integration events. All right, so now let's get specific about product create and update. So when a product is created in the catalog service, we're going to send out a product created integration event. And that event will have some properties on it that will indicate things like the product code and the product name so that the receiver of that event can then react to it and do what it wants with the data. And in our inventory example, we're going to be storing that data in the inventory database. So second bullet point is when product is updated in the catalog, we want to send out a product updated integration event. And then our inventory service will subscribe to and receive both product created and product updated integration events. And the inventory service will contain a copy of product information that it's extracting and then storing from those integration events. So, I was mentioning that we do not want to make real-time HTTP calls between microservices. So what I'm showing here is what the synchronous flow would look like if we were doing that. And again, at the top I put equals bad because this is not what we want to do. But this is a sequence diagram, and I also added numbers next to each step to show the ordering that the steps occur in. Anyway, some sort of UI, browser, mobile app, something is going to call the catalog service to say, hey, create a product, and here's the details about the product. It's going to turn around and insert it into its database, the catalog database, as step 2. Step 3, if we were not using integration events, is we'd want to now call out from the catalog microservice with an HTTP call to the API of the inventory microservice saying, hey, I also need you to create a copy of this product so that you have it in your records and you can start tracking inventory. Step 4, he would insert that into his database, and then we'd send a success response back to the catalog microservice from the inventory microservice. And then once all that happens, we can finally send a success response on step 6 back to the UI. So we're waiting on all of that to happen. And that can go horribly wrong, because what if our catalog microservice is up and healthy and working totally fine, but our inventory service is down? It could be down again because of required maintenance, an upgrade, unexpected outage. We want to be resilient. We really want to be able to support the idea of creating a product in our catalog microservice, even if the inventory microservice is down, and let the inventory service, once it recovers from its outage, be able to catch up. So this approach is not a good one because it would not allow for any of that flexibility. So what does an asynchronous approach look like? This is where we are going to use integration events. So again, it starts out the same. We send some sort of HTTP post from the UI up to our catalog microservice for creating a product. Step 2, we insert that into our database, the catalog microservice database. Step 3 is where it finally differs. Step 3, we are going to publish now our product created integration event out to the event bus. And now we do not wait. So you can see step 4, we don't wait to find out if anybody on the other end is listening or cares that we even put that event out there. And we're not waiting for any sort of response to say, okay, the event's been handled. We are right away on step 4 able to go back to the UI and say, hey, we successfully created your product. And if the inventory microservice is offline, then we've told the front end, hey, we created your product. We've logged it in our catalog database. And at some point, and hopefully it's almost instantaneous, but again, depending on the state of the inventory microservice, at some point in the very near future, the inventory microservice will also have that information. But you don't need to do anything, Mr. Front End UI client. We got it all handled, so we're going to tell you success. Step 5 is at some point later, the inventory microservice will, who's subscribing to product created events, will receive the product created integration event that was posted in step 3. Once he receives it, he will insert the product into his database. And then what he has to do is then in step 7, not let the catalog microservice know that it's been handled, because again, it's about decoupling. Inventory microservice doesn't know who necessarily put that event out on the event bus. The event bus acts as a middleman. And so the inventory microservice doesn't have to let anybody necessarily know other than the event bus that it's properly handled the event. Because once we take the event off the queue in the event bus, if we fail to insert it for some reason, we want to be able to reprocess that message. So we've got to let the event bus know when we have successfully processed that message, and therefore it can be marked out as closed, if you will. So that's what the asynchronous flow looks like. And you can note that I put the word better. I didn't put best just yet because there's still some things that can go wrong with this approach. There are 3 major problems that I want to talk about when it comes to asynchronous messaging, like what we just looked at. There's the 2-phase commit problem, duplicate messages, and out of order messages. And so let's start to dive into those a little bit. So what is the 2-phase commit problem? Well, let's say that, again, same diagram we just had up, but we get to step 3 and we publish our integration event and it fails. Like for some reason the event bus is down, or the internet or the network between the catalog microservice and the event bus has an outage of some kind, so we're just unable to publish our event. If we've already inserted the product in our database and we have a transaction going against our database, if we've already completed the transaction, then we have put the record into the database, but we did not successfully publish the event, and we don't want to ever end up in that state where we've inserted the record successfully in the database, but we never sent an integration event. Like, we need those 2 things to either happen and both happen, or roll it back. So you might say, all right, well, what if I have a rollback method right after my published product created integration event? Well, because we don't have a transaction that we can run between the catalog database and the event bus, let's say that we get to step 3, we send the event, and let's say it arrives successfully at the event bus and the event bus stores it. But we never get the acknowledgement that it stored the message back, so we assume the message did not get through, and now we roll back our insert. Now we've ended up with the opposite situation, where we've told the event bus this has happened, And so we've put out our integration event, but we never put it in the database because we never got the acknowledgement back, and we just assumed, oh, that must mean that the message did not go through. Therefore, I'm going to roll back, and we're in an invalid state. So you can, most messaging systems do not support a two-phase commit approach where you can actually run a transaction around both the database record and the event bus, making sure that they both either succeed, or if one or the other fails, they roll back together. So how are we going to solve this problem? The other thing you might think of is, well, what if we publish our product created event first and then we insert into the database? Again, you can have some of the same issues where if we publish the event to our event bus and we fail to get an acknowledgement back because of some sort of network outage or glitch, but it did successfully store the message, again, we're assuming that because we got no response that it failed, when in fact it didn't. It successfully got there. It's just the acknowledgement coming back from the event bus got lost because of a network outage or something like that. So how are we going to solve this? We're going to use something called the outbox pattern. And this is the solution to the two-phase commit problem. So we have transactions that we can run against a database, right? And if we do multiple steps within a database and we run them within a transaction, we can make sure that they all succeed, or if one or more of them fails, roll it back. We have that availability in the database itself. We just can't do that across the database and the event bus. So what are we going to do? We're going to write the message that needs to be sent. We're going to write that to the database when we're writing the product to the database, and then have a separate service that watches the database for new messages that need to be sent and is then responsible for sending them. And this will result in something called at least once delivery, which is what we want and what most microservices rely on and what most messaging systems are capable of. Notice there's really basically three options. You can have at most once, at least once, or exactly once. At most once means that it is going to arrive, the message you can guarantee will only arrive on the other end at most one time, but it says at most one time, which means it could get lost. So that would be more for like IoT data, if you're streaming data from devices, and if you lose a message here and there, it's not a big deal. In this case, we don't want to be losing messages, so we don't want at most once. What we want is at least once, and we can't get exactly once using this, and I'll show why. But there are ways that you could do it in things like Kafka, but it's really, I think, your best option is to use this outbox pattern approach with an at least once delivery guarantee. What that means is you might have duplicate messages. The same message might go out more than once, and we're going to talk about why that might happen and also how to solve it. So again, what we're going to do, and let's just fast forward real quick. I'm going to come back to the slide I skipped over. What you end up with is a situation like this. So this is where we're at our best situation. So step 1 is still the same. Step 2 is still the same. Step 3 is different. Step 3 is where we were sending our integration event, immediately to the event bus. Instead, what we're going to do is we're going to insert the message we want to send into a table in the database that is dedicated to storing, it's basically an outbox for messages we want to send. And we can put that in a database transaction to make sure that if the insert of the product worked, but the product created outbox record failed, we can roll that back. Or if they both succeed, we can commit the transaction. So now we actually are guaranteed, and we can commit that we've not only inserted our product, but we've also got the message we want to send committed. And then we can respond back to the client still on step 4 to say, hey, we got you, success. Step 5 then is through a polling mechanism, or we'll take a look at my preferred approach. There's different ways that we can look for and monitor this outbox table to know when we're supposed to be sending out an event. But something's watching that outbox table and says, oh, if a new record arrives, that means I got to send a message. So in step 5, I'm showing that something has pulled it and said, oh, there's a new product created integration event. Let me actually send that out to the event bus. And then in step 6, we're going to go into that outbox table and we're going to say, hey, we've successfully sent this message. So that means you could delete the message from the table or mark it as sent, a couple different options there. But we want to know that we've successfully sent it. So what this means, though, is let's say that in step 5 that we send the message and we end up with a situation I've been mentioning where we don't get the acknowledgement back. So we assume that it failed to get to the event bus. But let's say the event bus did store the message we sent, and the acknowledgement that we expected back just got lost on the network somewhere. The network went out. Well, then we could end up in a situation where we don't do step 6, mark it as sent, because we think it failed. And so later, a few seconds later, a few microseconds later, we might try again and send again. And this time we get an acknowledgement back and we update and say it's been sent. But in the process of doing that, we've actually sent the message twice. And it'll get queued up twice, which means the receiver is going to receive the event twice. And that's why it's called at least once delivery. Because we're guaranteed that we're going to get at least once of the message being delivered, but it may come through because of acknowledgements getting lost from the event bus on back, that we may accidentally send the same message more than once. So on the receiving side, we need to account for that. And let me come back to this, which is idempotent message handling, which handles two situations where we could receive duplicate messages via what I just talked about. And we could also receive messages out of order because, as you know, when things go out on the network, even though we send them out in a particular order, that doesn't mean they're going to arrive at their destination in the same order. So we could end up in a situation where events are actually arriving at the event bus out of order. So you could actually, in theory, end up with a product updated event that arrives before the product created event for the same product. So it got created and then updated on the catalog side, but the way the events arrive, it makes it look like an update occurred before the created. We want to be able to handle that. And idempotent message handling basically solves both these problems, which means we want to keep track of the last version of the message type process. So in this case, for product created, we want to track what was the last version, and we're going to increment the version every time. What was the last version we processed? So if the last message we got for product created was 20, the next one should be 21, and the next one after that should be 22, and so on. And by tracking that, we're going to know, is the message that we just received the one that we expected? If the arriving message is greater than the last version processed, then we go ahead and process the message because we know that it's a message that's greater than what we last processed. If the version on the message is less than the last one we processed, and that could happen if they're coming in out of order, then we do not process the message. So that kind of helps us with the out of order messaging. But we also want to construct messages where receiving the latest event means you can skip prior messages that might be lost or yet to be delivered. What do I mean by that? So let's say we have the situation where we have a create and an update of a product that happen almost simultaneously back to back, and we send out the events in the proper order. We send them out. The product got created and then it got updated, but they end up getting flip-flopped because of the network, and they took different routes to get to the destination and end up out of order. If the receiving side, in this case the inventory service, receives the update first, it should look in its database and say, do I have this product? And if not, let me go ahead and create it and update the properties like the product code and the product name based on what's in the message. And then if the create comes in afterwards, we should just ignore it because we don't want to overwrite what we just did with the update because that's the most recent message. We don't want to overwrite that with prior stale information that we've received. Another good example of this, if you think about a bank account, right? So if we're sending out a message every time a transaction occurs against a particular account, we probably want to send not just the amount it was adjusted by, like, okay, added $200 or removed $500. We want to send out the total deposit amount. That way the receiver knows what is the total amount that they have in their account, and they're not trying to add and subtract based on what's in the payload which if you're not processing every message, you could end up with an incorrect balance. So using idempotent messages, which idempotent just means if we send the same message twice, we're going to get the same result out. So if you think about it as like if we were sending messages, again back to the banking example, of deposited $10, and let's say that we end up duplicating that message by accident. We could have two events that arrive that say added $10, added $10, and if on the receiving side it's keeping track of the total balance and it's just using the incremental amounts it said in there, like, oh, deposited $10, it's going to end up depositing $10 twice, which is not good. That's going to be an incorrect balance. So what we want to be sending in the message is the balance, so that the client isn't trying to compute it itself and it ends up duplicating a message, that we're not going to have that situation. So we'll get into all of that more detail as we design all of our integration events to talk about that we want to design them and we want to design the way that they're handled on the receiving side to be idempotent. So back to our slide here, step 7. Once we get our integration event, we're going to insert the product in our database. We're going to update. Step 9 is new. We're going to update the product created last version processed. So again, we're keeping track in our inventory database of what was the last version or ID of the last product created message we got that we processed, and therefore we're going to record and keep track of that, so we know whether or not to process prior messages. And then once we do that, we're going to mark the product created with our integration event. We're going to let the event bus know that we're done. So one thing I should mention, by the way, is in our step 9 there, we want to be tracking that version number based on the ID of the aggregate root, right? So if the last message we got for, say, product 123 was 22, then if we also get a message for product ID 123, we want to keep track of what was the last message number that we processed for that ID, so that because we can't ignore events that are for 456 where the number might be 21. So if message comes in and it says, oh, I'm in the sequencing 21, if we simply look at, okay, is 21 greater than 22, we're going to say no, of course, and we're not going to process the message, where in fact we might want to process the message because the last one that we processed for that aggregate root 123 was message 22. Therefore we do want to process 21. So I think it'll become a lot clearer once we go into our coding examples. But that's really what we're trying to do to account for all the things that can go wrong in the asynchronous messaging. So again, we don't want synchronous approaches, right? We don't want what we started out with here, because we want our system to be resilient, that if the inventory microservice is down, that our catalog microservice continues to operate. And we want to be able to decouple these systems so that they don't necessarily even have to know each other exist and call each other directly. So we want to introduce our asynchronous approach to allow this decoupling and allow services to be offline and not bring down the entire ecosystem. But at the same time, that means we're going to use integration events. That introduces a new set of problems, really just around these 3 things: two-phase commit problem, duplicate messages, and out of order. And we'll be taking a look at that in a lot more detail when we actually write our code in our next video. Thanks.
Time for a shameless plug for my personal LLC, Keystone Code. I've been doing software development for 20 plus years now, and I've been lucky enough that I've played a lot of the different roles that go into software development, from back-end developer, front-end developer, full-stack developer, team lead, head of engineering, chief technology officer, business analyst, and architect. So if your agency or company has any needs across those different areas, whether it be a need from just understanding what those roles are, or have a need to fill one of those roles, either from a training perspective, a mentor perspective, or an actual hands-on perspective, feel free to reach out. So I can be reached at my email address, dmichael@keystonecode.com. or on the website at keystonecode.com. Thanks.